In this talk, you will find me avoiding using the word FPGA. It's short for Field Programmable Gate Arrays. And instead, I will adopt this more general notion of programmable hardware. I do this to give emphasis to an important divide between FPGA's past as a logic technology, as an alternative to ASICs, if you will, and looking to the future. Programmable hardware's future now as a computing technology, as what I hope will become a full-fledged third computing paradigm alongside of the traditional hardware and software ways of computing. This transformation from logic technology to computing technology has already been happening, right? Already, if you look around today at the latest commercial offerings, these FPGAs you see are not designed to be synthesis targets of an ASIC RTL netlist. Various special purpose hardened resources have been added to give each vendor's FPGA a distinct architecture and correspondingly separate application sweet spot. So depending on what your application is about, you will pick one of these FPGAs. What you develop on one may not work, or at least may not work well in another. And you definitely do not buy one of these FPGAs if all you wanted is an ASIC generically. These are FPGAs created with a purpose. And this new purpose is in computing. In looking to the future, the immediate question is how to make better use of FPGAs in computing. For the long future, we should be asking instead how to make better FPGAs for computing. What would they look like if they were created for the purpose of computing from scratch? For that, I'd like to share two visions about FPGA's future in computing. The first I title Programmable Hardware Becoming Fixture. The second I wrote down From Field Programmable to Programmable. It will hopefully mean something before the end of the talk. To be very clear, I am not here to make predictions of the future. I don't believe in that. I am here to advocate for what I believe to be the most promising future for us to capitalize on. With that, I'd like to set the context for this FPGA's new purpose in computing. A particularly important application area is in this thing I call network-driven data-centric computing that's happening in data centers, in data center servers. The balance of compute and data has shifted drastically from the old days of number crunching computing. Performance nowadays has a lot more to do with bytes per second than MIPS or gigaflop. There is almost as much value in simply holding onto data as in processing them. We are in a very different time. It is also the case in these data center servers, there is no longer really a center for the CPU to be central of. If anything, a data center server now has a front and a back. At the front door is the network. The network is what's truly driving what the server does. The CPU, GPU, and the likes are all reactionary resources in the back. It is in this context we ask, how can we introduce programmable hardware to make a better, more efficient server? It is no accident that I've drawn the FPGA in the position of the new front and the center of the server. Right? You'll also notice I have put FPGA in quotation marks. The reason is we shouldn't be thinking about a literal FPGA, at least not the kind that has to compete with ASICs to be the target of RTL netlists. The FPGA we're talking about will only have to be good for one purpose. In this role, in the making of a better data center server. If we get to put aside the almost 40 years of legacy baggage, what we want to keep is just FPGA's winning attributes. For the lack of a better word, I'm calling it FPGA-ness. How do we introduce FPGA-ness into the traditional server design doctrines, classically restricted to only hardware versus software? For FPGAs or programmable hardware to offer more than software, of course, we have to exploit FPGA's hardware-derived attributes. That means higher performance, better energy efficiency, and the ability to operate at individual bit and cycle granularity. On the other hand, very important in this iteration, programmability. Programmability shouldn't be something we have to apologize for to someone who really wanted an ASIC. This time around, right, programmability will be the key feature. It will be the reason we want to add FPGAs next to hardware and software in creating a better data center server. To see the future, it helps to step back into history. Right, this slide, the title says past, but really, even in the latest edition of Henderson Patterson, the idea of a computer is still centered around just hardware and software only. There is no place for programmable hardware, except maybe once in a while an FPGA is used to pretend to be hardware. That doesn't count. In this classic view of computer architecture, we are trained to do as much as possible in software and only resort to hardware where software is not good enough, be it in terms of performance, energy, or power. This was the way we built PCs back in the 80s. We haven't really moved away from this mindset. Now we're in 2021. Well, no, things have changed. Today, there are more and more things where software is not good enough. This is happening as we try to get still more performance under tightening power and energy constraints. To get more performance under power budget, we started to do more in hardware. The problem is that when you start pushing too many different things into hardware, hardware is not going to be good either. What should happen is the tasks that need to be done in hardware has to evolve after the hardware has been designed and already deployed. It is also very wasteful to want to build all the anticipated functionalities into hardware all at once if they're only used one at a time or only occasionally. So for these reasons, we are starting to see many examples of FPGAs being introduced into servers to make hardware smarter, so to speak. But so far, they're only ad hoc point solutions. Here, I've drawn a few examples, and we can make a few observations. Take Microsoft first. Microsoft got into FPGA because software wasn't good enough. When deciding between ASIC versus FPGAs as the answer, I don't think it was the case that Microsoft couldn't afford ASICs. They took the FPGA route because they needed programmability. So for them, FPGA was the unapologetic better answer. Another interesting example is Samsung. Samsung added FPGAs to their SSDs. In this case, is the difference more important that they made SSDs smarter, or they got to avoid the latency and energy to go all the way to the CPU in order to do every dumb little thing to data? Looking at this, if we step back, we can ask, how should it really be if we started from a clean sheet of paper? The picture I'm advocating for is a future where FPGAs are not just commonplace in data center servers, but becoming a permanent central fixture in the basic server architecture. I believe the opportunity is for an FPGA to sit at the center of the server as a crossroads of data, supporting intelligent data switching between server endpoints and providing inline processing on data that is on the move. It will do so in a programmable and active way without assistance of the CPU. It will lend its mark to all the hardware, so the rest of the hardware can go back to being single-minded commodities. We introduced this data crossroads FPGA not to displace CPUs or other processing means, whether hardware or software, but to augment what could not be done with traditional hardware or software-only options. Right? The goal here is to be able to manipulate data while they're traversing to minimize data movement and to reduce the amount of work, storage, or bandwidth that are needed at the downstream endpoint. In this role, the position of the data crossroads, because of the volume and speed of data moving through, one really cannot afford to stall or store the data. To do anything, you must keep up in real time. Software is out of the question. If you try to put an ASIC there, then we're limited to only the functionalities that we can fit onto the chip all at once, and only the functionalities we knew about at design time. So an ASIC, while fast enough, is a limited answer. This is the sweet spot for programmable hardware. I again use FPGAs in quotation marks, because while we want the reconfigurable solve logic for programmability, this data crossroads FPGA has a very definite purpose. And as such, it will for sure have a distinctive hardened architecture. For the function that are bread and butter to this role, it will be built with hardened support. So we're not talking about just another FPGA fabric, but it is a new central component as a part of a whole new server architecture. So you have to understand, right? In my mind, there will be nothing optional or peripheral about this FPGA. The right picture, right? The ultimate realization of this future is when we get a new socket on the motherboard. Right? When you get a socket on the motherboard, then this would have truly cemented the status of Fixture for this data crossroads FPGA. I'm getting a little ambitious, but it's not implausible or infeasible. And as I said, right, this is not a prediction. This is the future that I am personally working on today to help make it happen. So hopefully that got you to think a little bit, right? Yes, there are many issues to work out, many challenges. And so here, I want to get into just one particular aspect that I care most deeply about, right? It is in the programmability of FPGA, how to use it correctly, and to the fullest. So field programmable, right? Field programmable is a term used to mean you can make a gate array ASIC without a mask. You can do it outside of the fab. To an ASIC designer, this means no manufacturing NRE. Perhaps even reduce design NRE, because now you can iterate the design testing faster, more easily. But once the design is finished, deployed, and powered on, there's no more programmability. Right? The FPGA begins to live out the same life as an ASIC. This is a very wasteful way to use the programmability that we pay for. Right? Programmability isn't free. The same logic in FPGA is bigger, slower, more power hungry than an ASIC. If you use an FPGA as an ASIC, it will be a sucky ASIC. On the other hand, in light of what we said in the first half, right, it is time to stop thinking about FPGAs as the ASIC-wannabe, the ASIC substitute. In a computing FPGA, in an FPGA created for the purpose of better computing, let's move from the notion of field programmable to truly programmable. Right? This I mean programmable in the computing sense. You need to be thinking about the same kind of programmability we naturally associate with processors, with all the dynamism and flexibility that come with it. Let's use the programmability we pay for in FPGAs to do what we can do with ASICs. For that, we actually need to develop a whole new mindset for how to use programmable hardware and how to design for them distinct from ASIC hardware. To make this clear, we can ask a very high-level question. What is different when designing for ASIC versus designing for FPGA? This is not a trick question. Very simply, an ASIC design is fixed at design time. FPGA designs don't have to be. Unfortunately, to date, most FPGA designers are trained to think exactly the same way as ASIC designers. As an ASIC designer, when solving a design problem, an ASIC designer works out two basic things. Number one, what to include in the design. And number two, how much resource to spend on the different parts. So in this cartoon on the left, I'm showing a simple design with 3 modules, just 1, 2, 3. As an ASIC designer, or as an FPGA designer who designs like an ASIC designer, I would have done a good job if I correctly allocated the available logic area to the 3 modules such that I get the best overall performance. It is optimal if I cannot do any better for the same area. Well, this is optimal only if we ignore what can happen in the time dimension. Suppose modules 1, 2, 3 are only ever used one at a time. So on the right, I'm showing logic resources not as an area, but as an area time volume. I added a third dimension of time to the picture. Because the FPGA fabric is programmable, the correct way to do resource accounting is in terms of this area time volume. Under this interpretation, you can very plainly see a static ASIC style design is not the best you can do on an FPGA. An FPGA fabric is programmable. What a region of logic fabric is used for can change over time. So if modules 1, 2, 3 are only used one at a time, they should be mapped to reuse the same region by dynamic partial reconfiguration. For those of you who are not familiar with partial reconfiguration, it is a technology where a portion of the FPGA fabric can be reconfigured while the rest of the fabric continues undisrupted. This technology actually has been available for a long time. You just don't ask about it if you design for FPGAs like it's an ASIC. Let's use it. All right. If I use partial reconfiguration to reuse the same region for all three modules as shown on the right here, I could get the same performance as on the left, but now using less area. If you're an old-fashioned FPGA designer, you might ask, what about the area left over? Well, let someone else use it. Yes, right, there can and should be someone else. In a computing FPGA, just like how we multitask on a CPU, a computing FPGA can also be shared by multiple tenants. Alternatively, now on the picture on the bottom right, I can also make use of different, bigger, faster implementation of modules 1, 2, 3. They have the same functionality, just a different cost performance trade-off. So in this case, by using this other variant, I can use up all the fabric myself to get more performance. These are available to me. Even better, right? There is nothing that says I can have multiple variants of modules 1, 2, 3, all at different cost performance trade-offs. I can pick one set to use at daytime. I can pick another for nighttime so that I get the performance for the cost I'm willing to pay for. This is what I mean by using and programming FPGAs differently, meaning dynamically. And to start to design and think like this, it requires us to start to develop a very different mindset from ASIC designers. To share some experience with you. As we move into computing, the applications will become less regular and more data dependent, something that ASIC is not very good at. So in my group, we recently had experience of developing a rule-based network intrusion detection and prevention system on an FPGA SmartNIC. This is the Pegasus project, has some references on the slide. Among the packets that we have to handle, there is a wide range of behaviors in terms of how much work is needed and what resources are consumed. Fortunately, in practice, most of the packets we encounter will turn out to require only simple and regular processing. So we were able to build a very efficient design, getting all the way to 100 gigabit per second line rate on a single FPGA by optimizing to the simpler common case, even at the expense of the rare cases. It would have been hopeless to try to make all cases run equally fast. There's also no need to. There's a big gotcha, though. In this common case optimized design, what is the common case is empirical and only based on what we saw in the network traffic traces we used, without debating the representativeness of the traces we used. It stands to reason Company A and Company B's data center may not experience the same common case. Within one company, what is the common case during daytime may be very different from nighttime. And the cost that I'm willing to pay for performance is going to be different during normal operation and when I'm under attack. If you are making an ASIC for this, you get one shot. So you have to make the great compromise upfront, all at design time. If we're doing this on an FPGA, we have options. We should use it. So in the last year, we have been re-implementing Pegasus in what we call a programmability aware design style. It really just means that we are refactoring the original Pegasus RTL design now into a framework of plug-and-play streaming service nodes. The nodes are also parameterized, so instead of giving you one design, the new Pegasus 2.0, it's offered as a design template that gives you, the user, a space of designs to choose from. I don't need to be the person deciding what is the right design instance for you. The goal for the new Pegasus 2.0 is this idea of one deployment, one design. Each deployment of Pegasus should be able to use a design instance specifically tuned for the expected common case. This means for every deployment, depending on the size of FPGA that you're using, doesn't have to be the same as mine, and what you know about the operating conditions, again, could be different from my conditions, you get to set the tuning parameters for your deployment. If you can afford to spend 2 FPGAs on the problem, you should get to do that too. With programmable FPGAs, why should 2 different deployments ever have to be stuck with using the same design? It doesn't make sense. Okay? Now, on this second bullet, this is still in the research stage. We are also looking to allow a deployment to be able to change the design trade-off at runtime by using partial reconfiguration. In an FPGA that is shared by multiple tenants or applications competing for the available resources, I should have the runtime flexibility to pay for only as much or as little resources as I need to hit the performance requirements at any given point in time. So this is not how you would design for ASICs. This is how we need to be training the new generations of FPGA designers going forward. So this is the end, right? To sum up, very simply, my message is that the future of FPGAs will not be as an ASIC-wannabe. It seems obvious in hindsight, FPGAs offer something more than ASICs. Let's actually make good use of it, right? Especially in the context of computing. FPGAs or programmable hardware, they are still an underappreciated opportunity. We need to rethink fundamentally what programmable hardware can offer, not just as an ASIC alternative, but as a full-fledged third paradigm of computing alongside of hardware and software. And on this slide, I filled it up with some issues that I'm thinking about to use for when I need to use FPGAs in computing. I won't go into them in detail, right? Because they are also something new for me to still think through. This is really something for all of us to brainstorm together, right? Nothing about what I said is carved into stone. But if we work on it, we have the chance to make it what we want it to be. One more slide. Before I close, I want to acknowledge what I shared today is the common vision of my colleagues at the Intel VMware Crossroads 3D FPGA Academic Research Center. And this week's center was started just this year, and it was created to answer exactly this question. What is the role of programmable logic in future data center servers? If you have questions about this, I invite you to visit our website, or please just reach out to me or any of the PIs that's closest to you. Thank you. Thank you for your time.